So I'm going to talk about critical quantum sensing, and I'm going to talk. I'm going to address a problem that has been introduced a few days ago by Matteo Paris, in fact. And so basically, if you have some Hamiltonian and we want to estimate a parameter, and we have some freedom to add some other Hamiltonian term to estimate this parameter better, and what kind of Hamiltonian is the most suitable. And we are going to work under some educated guess for address this problem. And so we are going to choose some Hamiltonian that let the system undergoing a quantum phase transition, basically. And why this is educated guess is because basically if the system undergoes a phase transition, you have some divergence of susceptibility. So this doesn't guarantee, it's not guaranteed that you have some good performance in parameter estimation, because you have also a divergence of noise. So, but it's worth checking if this works. Okay. So, and one very topical example is the decay model. Okay. So where you have many atoms, and if you go to the thermodynamic limit, so the limit of infinite particles, so you have a critical parameter. So you have two phases basically, and you see that the ground state goes from some single blob to two blobs, superposition of two blobs. And so somewhere in between, somewhere around this critical parameter, you have some separation of the two blobs. So basically, you have some qualitative change of the ground state. So this means that you must have some divergence susceptibility if you measure some suitable observable. Okay, so this is very complicated. So we were interested in critical system with single bosonic mode. And one of those is for instance, a KERR resonator model. So this is basically it's a squeezing Hamiltonian with a frequency, and there is this KERR term. And here the thermodynamic limit, so the infinite particle limit, is replaced by a parameter scaling limit. So you retrieve the thermodynamic limit in the limit of small KERR, in the limit of KERR to 0. And you have basically the same phenomenology. So in the ground state, you have you pass from a normal phase, a single blob, to superposition of two blobs. But we will discuss what they're called the dissipative phase transition. So basically, the steady state level. So you still can observe phase transition when you have noise, when you have dissipation. And you basically, instead of have superposition, we will have a statistical mixture in the steady state. And okay, so we are interested in frequency estimation. Okay, so basically, So what we did is to compute. We sit at the steady state, so we wait the system to reach a steady state, and we compute the quantum Fisher information. And we saw that this quantum Fisher information scales quadratically with the number of photons when in the thermodynamic limit. And this we compared with the single photon drive. This we call two photon drive because it's two photon. And with the single photon drive, you in the steady state you will have at most linear scaling in the number of photons. Okay, and this was first result, and we wanted to test this in a superconducting device. And the reason is that in a superconducting device, the frequency is related to some external magnetic flux. Okay, so this can be used in principle as a magnetometer. Okay, so the simplest critical sensing product would be just to switch the critical pump to wait for the steady state and then measure and try to estimate the frequency. Okay, and okay, we did that. So we recently published a couple of experiments done by Guillaume in the group of Pasquale Scarlino in IPFL. So in the first experiment, we we characterize the two transition of the KERR resonator. So you have a second order transition here and the first order transition. So this is number of photons depending on the squeezing parameter on the pump. Okay, and you see clearly the separation of the two blobs. So here, close to the first transition, appears a metastable state here, the vacuum, and then it goes to a vacuum again. And then we just sit on the second order transition, and we try to understand how is the protocol, how this point is good for estimating omega. And so basically we retrieve the same plot, the same theoretical plot that we had, the same plot that we had theoretically. And we also try to understand what was the scaling with the KERR resonator, with the KERR parameter, and they scaled quite good, basically. Okay, so this was interesting, and we had experiment theory, but everything was done at the steady state. Okay, so what about? Okay, so first we also asked ourselves whether you can have an enhancement by having multiple KERR resonators. Basically, we consider multiple KERR resonator coupled parametrically between each other, and basically we saw that you have some superlinear scaling in M of the Fisher information. You don't have M square like usually happens in when you have coherently when you have a coherent interaction between them, but you have some collective scaling also here. Okay, and then we move to we ask ourselves, what about if we consider also time? Because this critical system, they are, okay, you have very nice scaling of the Fisher information at steady state, but to reach a steady state you need a lot of time because this so-called critical slowing down. So as soon as you go to the critical point, it takes infinite time basically to reach a steady state. And okay, so what we did is to compare two type of protocols. So one, the critical quantum sensing protocols, where we start with a steady state, then we evolve under the Hamiltonian, and then we measure. Okay, and then we compare this with the passive quantum sensing, where we first prepare for free some state, then we evolve under the just like omega A dag A. We basically rotate the state, and then we measure. And okay, so what we found is basically this. So the single shot QFI, you see that this is the passive protocol. It just goes to some maximum, which is of the order of n, and then it collapses because there is also noise. Okay, and while for the critical protocol this goes up, and you retrieve the n squares scaling the steady state, but you have a very large transient regime as well, where the scaling is like still like n square. Okay, but when you go to the multiple repetition, so you are when you reach the steady state, basically you measure, you need to repeat again. So you will try to understand what is the optimal time where to measure. So basically, what you do is to plot the quantum Fisher information rate, so quantum Fisher information divided by time. Okay, and you see that there are maximum points, so it's basically the optimal measurement point. And what we see is that passive protocols do better than critical. Okay. But as soon as we put some measurement or preparation time, basically this passive protocol they just collapse because because basically the optimal time in critical protocol is very large compared to it's basically infinite, and this is basically preparation and measurement time are basically negligible. And what we did is to compare with some quantum benchmark. So what we compute some fundamental bound, again, optimized over all possible strategies, most general strategies. So this basically is based on this paper from well, from Francesco Albarelli is in the audience, by the way, if you want to ask him. And this was basically this bound, and basically, well, you don't see it here, but this 2 is you can reach this bound with passive protocol when you asymptotically for a large number of photons. So passive protocols are actually optimal in this task. So, but okay, we learned something on this. We learned that passive strategy saturates a fundamental bound, okay? And critical strategy do not saturate a fundamental bound in this prepare evolve measure setting. But critical slowing down still allows for a coherent use of time. So actually it's a good thing, it's not a bad thing. And it's robust, so this makes the protocol robust to preparation and measurement time. Okay, so and what we found then is actually that okay, what about continuous measurements? And it turns out that continuous measurements are really good for estimation. And so what we consider is cavities, so some same KERR resonator. Okay, so this is still an environment, and so what we we consider is that the single photon drive. So basically, this it's a displacement in the cavity. And if you do some continuous photo detection outside, in this very weird limit, you get that the protocol is optimal. So for frequency estimation. So basically, you don't need any. Well, the only let's say quantum feature of this protocol is the photo detection. You don't need like squeezing or anything. The bad point of this protocol is that it's very unstable. So basically, in this regime, the photon current is basically 0. So if you have like a very slight bias on some parameter, it's just do very bad. And okay, what we discovered later is that critical protocol also saturates the bounds with continuous measurement. So this is a work is in preparation and in a more robust regime. Okay, and we did this. This was for frequency estimation, but in this paper we discussed also displacement, squeezing, all these things. We found the bound, the optimal strategy. So I invite you to read this paper if you are interested in this stuff. And okay, so this is a snapshot of results, and if you are interested, and collaborators. Thank you very much.